So I'm going to talk about enabling technology in the context of this mission concept. So very briefly talk about motivation and challenges, describe for you a little bit this long duration lander characteristics. I'll spend most of the time talking about the system status, the capability, what is this technology and how is it enabling, and a little bit about next steps. So this concept, the early work for it came from a study, I don't know if under planetary science smallsat studies. Some of you maybe remember that from a couple years ago. So it was funded under that activity. And this was our team there, a great team. I want to acknowledge their contributions, like I said, to the early concepts here. So this is an image that came out of that study that reflects the idea. Various sensors, small platform, about 1/2 meter, roughly 25 kilograms. And like I said, outfitted with various sensors, and I'll talk about the significance of those shortly. So I don't need to tell you all about why Venus is exciting to explore, so I'll skip all of that. The strengths, though, I do want to highlight that this concept is very much focused on the technology that it's enabled, or the capability that the technologies enable, and that is in situ operations at the surface of Venus for long periods of time. So the science that we're focusing on really leverages that aspect. So if you think about what would I do if I could live on the surface of Venus, that's what we're trying to do. So Venus seismicity, lithosphere structure and bulk composition, meteorology, chemistry variability at the surface, those are key parts of what we're trying to do with this with this mission concept and what the technologies that we're developing are doing. And it also contributes to rock and soil distribution, morphology, estimating momentum exchange, surface energy balance. So here's a science ladder. I won't go through this, but from a very basic version of a lander, a fully decked out version of the small lander, and multiple landers, you increase the science that can be returned from these concepts. So again, I won't spend a lot of time on this one. You know the technical challenges, but I'm going to point out that as we start talking about in situ, long duration operations, temporal things on the surface, another factor becomes important. So temperature has been the kryptonite of all landed missions to date, right? So no matter how big it is, shortly it's going to succumb to that temperature. So I'll show you how we deal with that one. So I think we're taking care of that. Another factor that comes in, it's not really a big deal at 2 hours, but it is a big deal when you're talking weeks or months. And you saw earlier, Noam had some of this evidence of some of these kinds of things happening on his fugacity sensor. So we've seen that also in other prior work. So these are the things that we have to think about as we look at longer operations on the surface. So what are the characteristics of this lander? So the technologies that we're applying here will enable operations of this lander for about 120 days or longer. So it's a Venus solar day. And the capabilities for this concept are actually built around an actual project. So in addition to just being an idea and a discussion of a mission, it's actually development going on under the Lizzie project. And that is the project that's developing all the various subsystems that really are part of SAVE. So basically this mission concept is called SAVE, Seismic and Atmospheric Evolution or Exploration of Venus, but the capabilities are being developed in real time, right, on this project called Lizzie. So the power systems, the avionics, the sensors, those are all being developed under the Lizzie project. So this is more than a concept, it's actually being worked under a different name. So our approach, so how are we tackling this temperature problem? So rather than trying to thermally manage and control various aspects of the mission, or the internals or the spacecraft or this lander, what we're trying to do is take decades of experience that we have in high temperature electronics, sensors that we've been using in the aeronautics industry, jet engines, harsh environment, high temperatures, and apply them to this Venus problem. So we have electronics that are based not on silicon, but silicon carbide, so they can operate very comfortably at temperatures at the Venus surface. So all of the systems, everything on this lander, with this caveat I'll mention in a minute, is designed to be running and operating in the Venus temperatures, in the Venus pressures, and with the chemistry that we're going to see. So temperature, pressure, chemistry, radiance, seismicity, these are all designed, as well as the subsystems, the power systems, like I said, the processing of the data, the communication systems, the structure, all of that is designed to be happy in that temperature. That's how we're solving this problem and using decades of experience to do that. The one aspect that is short duration is for the seismic, for the SAVE concept. We did have cameras in there, and so to date, we don't have a high temperature sensor detector. But I will point out that there's some work going on. Jeff Berserski is a PI on developing a high temperature photodiode, and he can talk to you about where that stands. There's been some nice progress there. But for the SAVE concept, this was a short duration. You take some pictures, you get the data off, and the camera dies. So, but everything else continues. So the lander, I think I mentioned earlier, is 25 kilograms, operates for 120 days or more. It's about 50 centimeters, half a meter at its widest point. This is a block diagram of what it looks like, and there's some images of, like I said, real hardware that's being developed. So these are sensors external to our main structure. There's antenna work, seismometer. This is actually not developed on Lizard, it's under a hot tech. These are internals and how things work together, fit together in terms of the processing. So I won't go into more details here, but that gives you a little bit of clue as to the different elements that are. Memory was not part of the SAFE concept, but it is in development under hot tech. That would be a nice enhancing feature, so that's also shown here as a potential enhancement coming down the road. So this is where I'll spend most of my time. Top level status. So Lizzie, the project that's actually doing this, has made tremendous progress in the last few years. I've been working on it. And again, SAFE uses these systems. So what is this progress? So first thing that we've been spending a lot of time on is taking the electronics that we've been using in aero applications and applying them to this. So we've taken electronics that maybe increase the complexity from maybe 20 or so devices, discrete devices on an IC to over 2,000 now. And we've had them in ovens at 500 C running for thousands of hours, and they continue to function. So this is a long process to run a generation. We're on generation 12 right now, and we're in fabrication. And so in the next few months, we'll get through that fabrication process, and hopefully we'll have something more to share about the outcome of that and our ability to execute the mission as designed here. High temperature batteries. So we have developed with some partners a full voltage battery that we've tested under the loads that we would see on this lander. It was designed for 60 days. We've had them running for 120 days. So we feel confident that we have the power system to execute this mission for the timeframes that we're talking about. We've now transitioned the work from the actual chemistry and the ability to work at those temperatures into more of the mass reduction, packaging, robustness to anomalous impacts and things like that. So that's where the focus has gone in terms of the batteries. In terms of high temperature communication systems, this is our tall pole. This is where most of our risk still lies. Part of that is in terms of material selections. The antenna has the whole comm system has a difficult challenge. So part of it is just having the ability to make the antenna materials with the right dielectric properties that can withstand the chemistry and those temperatures and operate in a predictable regime. And so, so we've made a lot of progress on that as well. We just are coming out of a test in our gear facility, which will hopefully confirm that we have that part linked. The next thing is in the comm system, we also have to develop a different type of transistor architecture than we're using here for the signal processing. And we use that for power switching and to get to the frequencies that we need for the comm system. So we're basically using the same techniques and capabilities infrastructure, but we're actually building a different device architecture, transistor architecture for this. And so we've developed that, but we're in the process of assessing. So again, we'll have more to share about that in the coming months. High temperature instruments and sensors. Those are in various degrees. We're not currently funding our instruments. We're putting our energy and resources into this. But we have had, I got 1 minute. So we have had a lot of progress, and under hot tech, we are developing this seismometer. So that's being developed under different things. And we have many of these operated in Venus conditions for months at a time already. So the precision and the performance is what we're focusing on now. So this is how it all flows together. I won't really talk about this too much, but you can see the various parts come together. This would be our completed Lizzie, and then the things that added to it are the SAVE, and then eventually it needs to match up with an orbiter, which we'll have to communicate to. So next steps, continue maturing our technology. If we had the resources that we've had up till now, we can probably be ready, we would be ready for a mission in the late 2020s. We have existing hardware, we're doing tests, and we have continuing funding on development of the seismometer, which is a key part of our science package. So that's That's it.